Okay, today we're going to talk about making clouds and precipitation. So, clouds are basically water that's condensed in the atmosphere. Uh, so, you would think that, oh, this is going to occur all over the place all the time because we have so much water, especially over oceans and all. Well, it takes, as you learned last time, it takes a lot in the last chapter about moisture and stuff. It takes a lot of moisture sometimes to reach the level where the air can't hold any more moisture and it just begins to condensate out. So with that in mind, there's another problem. When the water vapor begins to condensate out, it forms very tiny little droplets. These droplets might be only 0.001 micrometers. They're extremely small. And in order for them to grow, the saturation vapor pressure literally has to be 340% relative humidity to continue the growth of that droplet. So something else must be going on. I guess I could relate it to today's things that are happening with COVID. And we all hear about masks and wearing them and droplets and all that are formed when you breathe. Well, the reason those droplets are so tiny and never grow is because they're obeying this principle. Those droplets are small because they literally have such strong curvature that the water vapor tends to escape out of them and they can't grow. Doesn't mean they can't cause problems otherwise, obviously, but that's why the droplets that come out of your mouth and stuff don't become big rain droplets or anything. And that's why even in wintertime, when you see yourself, this breath out your mouth, when you see all that condensation happening and you see like smoke coming out of your mouth, they don't get bigger because they're little tiny droplets. And all that curvature with the kinetic energy of those molecules in them keeps it from growing. Now, there is something that allows it to grow, and that's called condensation nuclei. They can come from anywhere. They can be salt, particularly around my house where I have an ocean. In your central Ohio or in Ohio, there's lots of dust that blows up out of the ground sometimes. They can become condensation nuclei. When that happens and that attaches to these droplets, what happens is they become much more readily available to grow. Condensation can occur much easier on these kind of a droplet. So that's why you see the clouds in the sky, because you're getting this roll of these nuclei. Oh yeah, there's another thing. Think about it. When the droplets are growing, they have a lot of kinetic energy. And as they reach freezing, they're still pretty small. So what happens is there's so much kinetic energy in them that they don't freeze at 0 degrees Celsius or 32 degrees. They got to go way down below that to freeze. So you would think, oh, you'd never see ice in the sky. I mean, really, to freeze, if there's nothing else helping it, water vapor has to get to minus 39 degrees Celsius. That's cold. So there is something else. We talk about water cloud condensation nuclei. Well, there's also ice-forming nuclei. And these ice-forming nuclei, very similar to cloud condensation nuclei in their makeup, a little bit different chemically, but they allow the water to freeze. And it usually starts freezing around minus 9 degrees Celsius. So sometimes in the wintertime, when it first becomes winter, we'll say, the air temperature aloft might only be maybe 10 degrees, about 15, 20 degrees sometimes. And you wind up literally having very super cold water droplets in the sky. So you don't have any of this freezing yet going on. So one of the things sometimes you look for is to see if the clouds begin to change texture. If you look up at cirrus clouds, they look different than the big bulbous low-level clouds sometimes. And sometimes you can even see this minus 9 degrees Celsius reached, and all of a sudden there's a big, massive amount of snowflakes literally forming in the clouds, or ice crystals. So now you see how these clouds begin to form. They literally need condensation or ice nuclei to form them. So with that, we'll move on here a little bit to we talk about cloud classification, and you can read it and see it in the table that's in your chapter pretty easily. So I won't worry about boring you with talking about all the different kind of clouds that are out there. I love to watch clouds, and I can spend days doing it, and I have. And there are all kind of unusual shapes of clouds and unusual looking clouds, and fog, of course, just another cloud that's really on the ground. We'll talk about that some more. And we talk about moisture advection and how literally fog can form over the water, move over land. I was attending a high school football game in Florida when I was at Florida State one time, and fog literally started coming in off the Gulf of Mexico. And by the second half, you could not see the players. And I was just standing on the sidelines watching it. And literally, the fog got so dense it was hard to walk back to the dorm that night. So another thing with now we take these clouds, we want to have precipitation come out of them. So what happens is gravity pulls down like a snowflake, and that snowflake has to weigh so much to begin to fall. And gravity will grab it. But then there's air, there's friction. We talked a little bit about friction when we were talking about wind. Well, it happens here. So they literally balance the forces. The size of the snowflake, balance of gravity pulling on it, pushing it down, air resistance pulling it up, causes eventually a terminal velocity, so that literally snowflakes have a velocity that is pretty constant when they're falling down to the ground. Raindrops do as well. Now, maybe the bigger raindrops might fall a little faster. Hail, it's another one that would have a terminal velocity. It all depends upon the mass of the object. That's what that is. And you can actually see some of the terminal velocities there. So how does precipitation form in a cloud? There's two processes. There's collision coalescence in warm clouds, and there's a Bergeron-Findyson process in cold clouds. Guess what? You live in the mid-latitudes, 90% of the precipitation you experience is caused by the Bergeron-Findyson process. Every once in a while in the summer, you're going to get warm clouds and collision coalescence. Tropical Storm Faye that went up the coast had a lot of warm clouds, collision coalescence rainfall. So one of the things with collision coalescence, we'll show you here, is it's all about a little tiny droplet begins to grow, maybe a little faster than those around it, and begins to fall. And what it does, it bumps into other raindrops, little dots, and grows bigger and bigger because it absorbs them, till it eventually reaches a point where it's big enough that it can fall to earth. So there's got to be a lot of moisture in the clouds, and we know that warm clouds hold more moisture than cold clouds. So that many times when you get into this warm cloud situation, you get some of the heaviest precip you're ever going to see. Some tremendous downpours can occur. But the raindrops may only be very small because they bounced around inside these clouds so much. They haven't really picked up maybe a lot of the moisture. There's so many of them. There's all over this map, maybe another raindrop forming. So that's basically the collision coalescence process, one that occurs in warm clouds. Bergeron-Findyson occurs in cold clouds. Cloud temperatures usually got to be around -8, -9 to begin it. What happens is ice crystals begin to grow. Say there's one form here, one form there. Well, what did we learn? We learned that in the last chapter that the relative humidity, saturation vapor pressure, is less So the relative humidity is greater over ice. So with the saturation vapor pressure being pulled from the rain area towards the ice, so the water is literally going from these raindrops towards the ice crystals are growing. So eventually you wind up with all ice crystals and no raindrops left. But that's where you get most of your precip process occurs, and these ice crystals get big enough, they fall down. They melt on the way down and produce rain many times, but they could stay as snow as well. So that's how all these fancy precipitation falls. You can go through all kind of precipitation. There's all different types of it, all different diameters of it, rain. But one of the things I did want to touch on with snow was snow can look literally what they call dendrites, what they call prisms, thin plates, big dendrites, or even other things if it's colder. And when you're trying to forecast snow, you know there's air packed into little pockets around snow when it falls. We've talked about insulation to ground. Well, part of the process is figuring out what type of snowflake is going to fall. So where in the cloud is most of the precipitation developing and going to fall from? And depending on that, the same amount of moisture might produce these solid prisms and may only give you 2 or 3 inches of rain, of snow, or it might produce a dendrite, and instead of 2 or 3 inches, you wind up with 6 to 8 inches. So you see, that's another aspect of trying to figure out just what type of snowflake is falling. So with all of that today, we're going to talk about, I wanted to just show you quickly a couple images here. Here's what's currently occurring across the U.S. This is a lightning and a visible satellite geo map satellite. You can see over here is Ohio, and there's some showers and thunderstorms. There's some more Indiana coming into Ohio with the lightning there. So, and we talked about sea breeze fronts, and you can see the convergence along one here in North Carolina, where new lightning is beginning to pop up and new thunderstorms are beginning to develop. So I wanted to show you, we talk about radar this week. Radar is just sending out a pulse of microwave energy, and guess what? Less microwave energy is emitted from a radar than if you were standing next to a microwave. So there's hardly any, very small amount of energy really emitted up there, but it detects raindrops or anything else that it can reflect off of and bounce back. And here you can see it real time in Ohio, southwestern part of Ohio here, into Indiana, and the red being more reflection. So the more raindrops, the more reflection. Oh yeah, and sometimes radar can actually pick up literally what they call boundaries in the sky. Maybe they're a cold front, maybe they're dust storms. But radar will reflect off of dust or off of bugs if you have enough of them around. I saw one the other day went up in the south across my house, and the wind shifted to the south as it came by. And it was literally probably bugs that it was seeing, but it did pick up that wind shift. So radar is really very sensitive. But it can also pick up velocity. You've learned this week about radar and Doppler velocities and stuff. Well, here's a Doppler velocity right now, and they basically have northwest winds coming towards Cincinnati. Wherever the radar is, the winds you're picking up are towards it, always. They're always going to be perpendicular to it, but by adjusting that knowledge, we can determine how the winds are. There's not a lot of wind here today, it looks like, in this area, so they're probably not real fast moving. We can take a lot of information from radar, and one of the products is what they call multi-sensor information. Radar is now in dual pole mode. What does that mean? It means I can see the radar in several directions. It's not just a horizontal beam, but it's also a vertical pulse. With that, I'm able to do something called differential reflectivity. Basically, I'm looking at the size of the of whatever is reflecting back to me. And here is hail being detected by reflectivity. A little hard to tell if it's hail or not. It could be very heavy rain. But here it is on differential reflectivity, and you can see there's a change in size in this area, all the way down to blue, which is really a big monster drop of some type. So when it knows that there's a change in size, it's a really great way to identify hail, and dual pole does that. With that as well, you can identify debris sometimes and all, but sometimes when raindrops change shape, you can actually look around them and see, well, are they being correlated to each other? How does the shape of this raindrop correlate to the shape of this one? And when there's a fast change to shapes, you're getting things like wind updrafts. We've talked about updrafts and thunderstorms and all. Very strong vertical motion there. Or the freezing level. When rain is beginning to change into ice, there's a lot of mixed shapes within it. And back here, it would be all snow, for example. Or out here, excuse me. Back here, it would be all rain. So you can see there's a change in shape. So you can actually see the melting level with this. And we can put all this together and generate literally hail swaths, look at radar, look at rainfall. All of this information can be composited, and we can actually see it around areas and try to do a job of forecasting for what you're going to get in the next couple of hours, so we can warn you about severe weather. So hope you got a little bit out of this. Let me know if you have any questions.